Welcome to Advanced Linear Algebra. In the very beginning, let me raise 3 questions. Why one has to study this course? What we are going to learn from this study? What will be the mode of learning this subject? The first question is basically what is the motivation behind this study? As you will come to know, the basic concept of linear algebra acts as a prerequisite in many courses, undergraduate, graduate and postgraduate levels also. It may be from mathematical science, engineering science, biological science, even in sociology and economics also. Frequently, one has to encounter the system of linear equations and the question concerning to it, existence of solutions, and if it exists, how to find. Similarly, system of differential equations, how to find the solution of it, if at all solution exists, how to know the behavior of the solutions, characteristic, etc. To know all these things, one has to use the concept of linear algebra. So, it is a very essential subject for many courses. Regarding the second questions, what we are going to study, that is basically course content. As you know, in last 2 decades, the advances in linear algebra is so vast. It is very difficult to consider what will be in a course, time limited course, and what should not be. Anyhow, we have designed the course in such a way that if someone has done this course, he or she will be in the position to face the challenges in linear algebra related applications in their different courses. Based on that, this present course consists of 7 modules, start from linear system of equations, vector spaces, linear transformations, and the end singular value decomposition theorems and its application also. Regarding the last questions, what will the mode of learning these subjects? It will be through series of lectures and solving assignment sheet problems which we are going to supply you. You have to solve it. While solving, you may face some difficulties. We can have some email conversations or even by telephone conversations with the 2 teachers in this course and with me also. Throughout this course, I will use most of the lectures will cover from the basically linear algebra by Hoffman and Kunz. Other parts I will let you know in time to time, please. So, before starting the first modules, let us quickly recall the properties of complex and real numbers with respect to binary operation addition and multiplications. As you have already learned that complex number or real number satisfied certain properties. So, let us represent complex number by the symbol C and real number by the symbol say R. The properties what we are going to talk for the complex and real numbers, this is basically same sort of properties. So, let F represent either complex number or real number. Now, let me talk about the properties with respect to additions. So, properties with respect to addition. For the any x, y, z belongs to capital F, the first one closure property, for x and y belongs to capital F, x plus y also belongs to capital F. Second one, associative property x plus y plus z equal to x plus y plus z. Third one, existence of zero element. You know, 0 belongs to capital F, it belongs to a complex number as well as it belongs to real number, and for any x belongs to capital F, 0 plus x equal to x plus 0 equal to x. Fourth one, existence of inverse. For any x belongs to capital F, minus x also belongs to capital F, and x plus minus x equal to 0. Commutative property, that is for x and y belongs to your capital F, x plus y equal to y plus x. The set which satisfied this first 4 axiom is called the abelian group also. With respect to multiplication, capital F satisfied 6 more axioms or properties with respect to multiplication also. The first one is closure property. That is for x and y belongs to capital F, x into y also belongs to capital F, please. For sake of simplicity, I will write down simply x y, or x into y belongs to capital F, please. Here also associative property holds good. Associative property, that is x into y into z equal to x into y into z, for x, y, z belongs to capital F. Third one, existence of unit element. element 1 basically. See, 1 belongs to capital F, it may be from complex, it may be real, but 1 belongs to capital F. And for any x belongs to capital F, 1 into x equal to x into 1 equal to x. So, not to confuse, if you want to star, this is fine. Fourth one, existence of inverse for any 0 not equal to x belongs to capital F, there exists 1 by x such that x into 1 by x equal to 1 by x into x equal to 1. So, this 1 by x belongs to capital F please. So, even though I am not writing star, but it does not mean that I have not written any operation, I am writing simply x into 1 by x, and which is equal to 1 by x into x please. Here also commutative property holds good, property also holds good, that is for x and y belongs to capital F, x into y equal to y into x. Finally, distributive property over addition also holds good, that is for x, y, z belongs to capital F, x into y plus z equal to x into y plus x into z please. So, with respect to multiplications, the set capital F is a first group because satisfied all these 4 axioms of the group. It also satisfied the commutative property, so it is an abelian group. And the last one's distributive property over addition please. With this informations, let me define one terminology called the field. What is field? Field, it is a non-empty set capital F equated with the 2 binary operations, say addition and multiplications. It is said to be field if with respect to addition it is a group, and with respect to multiplication it is an abelian group, and distributive law over addition also satisfied. So, this implies the set C, the complex number is a field, real number is also a field. One can also check the set of rational number. Rational number is also a field. But interestingly, see the Q which is subset of R, and R is subset of your C, and Q, R are non-empty subset also, and they also satisfied the definitions, I mean all the axioms of the field. So, here Q I can treat that as a subfield of the field Q, R please, and Q R is a subfield of the field capital C. So, what is the definition of the subfield? So, subfield I am saying that it is a non-empty subset F prime of the field capital F, which satisfied also all the axioms of the field capital F, then only I will say that the non-empty subset is a subfield of the field capital F please. Throughout this course, I will consider capital F as field for my rest of the lectures, the lecture please in this course. Now, introducing the definition of the field, subfield, let me consider our first module, that is system of linear equations. What is system of linear equations? It is basically a problem of finding n variables x1, x2, xn, where each xi, xj belongs to the field capital F. That field may be set of complex number, it may be real number also. And this n variables satisfied each equation. There are m equations which I have written here in star, that is that I have written m equations a11 x1 plus a12 x2 plus a1n xn equal to y1, a21 x1, a22 x2 plus a2n xn equal to y2, and similarly am1 x1 2 plus amn xn equal toym. Here aij and yi all belongs to the capital F, where 1 less than equal to I less than equal to m and 1 less than equal to j less than equal to n please. Any set of equation can be defined as the system of m equations in n unknown. One can define it as a m equation, system of m equation in n unknown please. When the right hand side of this set of equations are 0, we should say that the system of m equation is homogeneous, otherwise it is non-homogeneous please. And any n tuples x1, x2, xn for xi belongs to capital F 1 to and I from 1 to n, if satisfied each equation of the m equation in m unknown system, then I will say that this n tuple will be solution of the system please. Now, let us try to understand the solution as well as existence of solutions from our elementary 11-12 concept also. Then I will go for the generalization case please. Let me take very simple examples, that is 2x1 plus x2 is equal to 4 and x1 minus 2x2 is equal to minus 3. So, geometrically what I can see it here. So, this first equation is nothing in the x1 x2 plane. If I consider this is x1 and this is my x2. So, in x1 x2 plane, the first equation represents basically a line. I can simply this one. Okay. So, when x1 equal to 0, that is equal to this point, and x2 equal to 0, that is 2. So I can say a line is like, the first line L1, this is L1, and second one say that x1 equal to minus 3 here. So, and when x2 equal to 0, x1 equal to minus 3, so this point, and when x1 equal to 0, it is 3 by 2, so it will be here, 3 by 2 means here. So, it is something like this. So, this is my L2, this is my L1 please. Now, what is the meaning of the solutions? Solution is basically intersection of these two lines. Now, these two lines meet at the point here as a 1 and 2. You can check it, this is 1 and 2 please. Yeah, I see that satisfy this one please. Okay. So, if these two lines are, if they are parallel, then certainly we will not get solutions. So, the existent solution depends on the whether lines are parallel or they intersect each other or not. It may be possible that two lines also overlap and lie on each other also. So, then also system solution have solution please, but if they are parallel, certainly no. Similarly, if I go for the next example in my 3-dimensional space, say x1, x2, x3, we see that I have considered 3 equations here. Now, the first, each equations represent a plane, x1 plus x3 is equal to 2, means it is a plane parallel to x1, x3, x1, okay, x1 O x3 plane please, where x2 is perpendicular please, you can say. Now, similarly, x1 plus 2 x2 is equal to 3, it is another plane and in 3-dimensional space. Similarly, third one. Now, this system will have solution provided not a single plane is parallel. If one plane is parallel to any of these two, definitely this system will not have solutions. Existent solution depends on whether planes are parallel or not. Now, let me represent again, let us discuss this issue in a bit different notations. Different notation means one can see the same, let me consider same equation, that first example, I will also consider second examples. Let me see solution of these systems in a bit column structure. What I mean to say you, the same equation one can write down x1 into column 2 1 and plus x2 into column 1 minus 2 equal to 4 minus 3 column please. Now, if I represent this 2 1 column as my vector, say u vector, and the 1 minus 2 as a v vector please. So, these equations represent basically some sort of linear combination of the vector u and v, which will give me another vector on the right hand side please. So, if I quickly sketch it, okay. So, what I have done, so let me consider here, this is my x1 and this is my x2. Now, I am writing the vector u, let me consider u is equal to as a your 2 comma 1 transpose, I can say that column vector type of things, or if you recall our 11 12 as vectors having in say force velocity there is a vector. So, we can write in 2I plus 1j type, that is also possible please. But anyhow, I hope you will not confuse with these notations. So, let me write the vector u equal to 2 comma 1. So, this means that okay. So, this is the basically the vector u vector having coordinate is basically 2 comma 1. Then another vector v is equal to, I am saying that 1 comma minus 2 transpose. So, this 1 unit this side and 2 units bottom 1 and 2 here. So, it is here. This is my v please. Okay. So, these two vectors. Now, suppose somehow I know that for x1 equal to 1 and x2 equal to 2, it is a solutions, x1 equal to 1 and x2 is equal to 2. Suppose these are the solutions, let me see it, what does it means. So, this is u. So, let me write down here also, sketch it. So, first is 1 2 1 unit, yeah, this is my u, then it has gone to the next is uv. So, it will be something like this. then 2 times of it. So, I can extend it, it will see that this point is going to basically 4 comma minus 3. So, 3 units from the bottom and this side is again 4 units please. So, this means that this one, yeah. So, one type of u, 2 times of v equal to this one. Okay. So, this is basically your right hand side vector. So, this means that we are looking for the possible linear combinations of u and v which will give right hand side vector. So, this is, let me consider w please, which will give w please. So, you may have linear combination, possible linear combination for which you will have 4 and right hand side vector, you may not also. Now, the question is still remain unsolved please. So, it is not, we have not answered, we are just explain the meaning of existence of solution for this system please. One can also represent for the second examples over the 3-dimensional space, that what I consider here as a x1, x2 and x3 over this also. You will see that here also we are looking for the possible linear combination of the u, v, w which will give me say something z. You may have solutions, you may not have solution please. Now, still under what condition this system will have solution and how to find solutions, this is still left out please. That questions how to know whether a given system of linear equation has solution or not, and if yes it has solution, then how to find it, this question we are going to answer please. Certainly one has to follow the elimination procedures what we have learned in our 11-12 also. In the elimination procedure, when we are eliminating one by one, exactly what we are doing? We are basically doing some linear combinations of the given systems and introducing another system please. So, what is linear combination of equation? So, if I recall my system of equation star, that is a11 x1 plus a12 x2 plus a1n xn equal to y1, a21 x1 plus a2n xn equal to y2 and am1 x1 plus amn xn equal to ym. If you recall these systems of equations which I have considered as a star, multiplying 0 not equal to C1, 0 not equal to C2 and 0 not equal to say Cm to first, second and mth equations respectively and add it. We will have a new equation of the form of like I can write down say sigma ai1 into I equal to 1 to m x1 plus sigma ai2 I equal to 1 to m x2 plus will have sigma a I n and I equal to 1 to m and x n equal to will have sigma c I and y I equal to 1 to m. So, I will have a new equations as a linear combination of the equations of star, which is called as linear combination of equations of star, please. Even if I want to multiply the first equations by some constant c and get a new system, there I am getting basically linear combination of the existing system, and through these procedures I can write in a very generalized form, and from the system star we have obtained again m equations as a linear combinations of the equations of star, and we have a double star. Here also I am getting that m equation, please. Here also all bij zi belongs to the field capital F, and 1 less than equal to I less than equal to m, 1 less than equal to j less than equal to n, please. I will say that these two systems star and double star are equivalent systems. Equivalents provided the equation, each equation of the one system has been obtained as a linear combination of the equation of the another system, please. So, I can say double star and star are equivalent system, please. Now, certainly there will be questions whether both this system will have same solutions. Answer is yes. Let me take very simple examples. Let me consider say a11 x1 plus a12 x2. So, this is equal to say y1 and a21 x1 plus a22 x2 equal to y2. Now, if I multiply the first equation by some constant C1 to both the sides, question is whether system will be changed. I mean system will be changed, but do you think the solution will be changed? Now, if I multiply some constant C, suppose C1 to the both the sides, left hand side of this ones, then we see there is no change. This line, this is at say line 1, this is line 2. So, the line 1 and line 2 will remain as it is, even if you multiply some constant C1 or C2. So, similarly in 3-dimensional space, suppose if I consider two plane say a11 x1 plus a12 x2 plus a13 x3 is equal to say y1 and a21 x1 plus a22 x2 plus a23 x3 equal to y2. Here each of this equation represents a plane in 3-dimensional space. This is P1 and this is say P2, plane 2, plane this one. Now, multiplying by some non-zero constant to any of these two equations from both the sides, it does not change the plane at all. So, all the points on the plane will remain same, please. So, by this process, if I multiply suppose from this getting I am multiplying C1 to say C2 to this is system 1, and suppose I have got the new system is as a B11 x1 plus B12 x2 plus B13 x3 is equal to say Z1 and B21 x1 plus B22 x2 plus b23 x3 equal to say z2, where I have multiplied C1 to say first equations, but second equation I have kept as is it my previous one P2. So, now this system is a new system, but both this system again giving me the same plane what I have introduced in my first system. Existence of solution depend whether this plane are parallel or not. If they are parallel, certainly there will be no solutions. If there is no parallel, then certainly they will meet, there will be a common point, so we will have a solution case. Now it is true for first case, even for the equivalent system case also, equivalent system case also. So solution will not change, please. Okay. So what we have learned so far? We have learned what is system of m equation in n unknowns, what do you mean by solutions, and what is the geometrical meaning of the solutions in our existing concept, what we have learned in 11-12 through the vector structures, through the geometrical structures, and what is equivalent systems, and we have seen that equivalent systems have the same solutions.